So hello, my name is Asaf. I'm a faculty member at the Department of Software and Information Systems Engineering at Ben-Gurion University. And my talk will be on adversarial learning in cybersecurity, or in other words, how to attack or defend against attacks on machine learning systems or processes. So, okay, so in general, my research since 2005, when I joined the university, is around the cybersecurity domain, and mainly how to utilize machine learning in order to solve different problems in cybersecurity, such as malware detection, like the problem that Ishai was just presented, how to profile users in order to understand how vulnerable they are to different attacks, protecting avionic systems, apply machine learning in order to detect attacks on network infrastructures or of airplane, and many other problems which machine learning can help in solving. Throughout the years, I also created 6 years ago a course which deals with how to use machine learning in cybersecurity, and when I searched for topics for this course, I encountered one of the topics which was relevant but also minor back then, was adversarial learning. However, through my research, and especially in the last couple of years, we can see a trend and in the understanding of the importance of understanding how to protect machine learning systems against attacks. The main reason is the industry companies are utilizing and integrating machine learning in their business processes, not only for cybersecurity. And attackers understand that this can be a target in order to achieve their goals, into compromise systems and make or harm the organization. And attackers are trying to find actually vulnerabilities or loopholes in the machine learning process in order to attack these systems. If we think about it, attacking or fooling AI systems is relatively easy, because eventually the machine learning or the model that is being trained from data that is exposed to, that's available to. It does not really have the ability to reason, and attackers can abuse this assumption or this fact in order to attack the system. This is also, you can see this trend in academic publication. I just extracted it from Google Scholar, and you see basically from 2016, a dramatic increase in the number of publications that deals with adversarial learning. And again, I think that the reason for this, and if you can see the number for 2018, you can see almost 5 or 6 publications per day in this domain. And again, the main reason is the integration and increasing usage of AI in the industry. And also, it is not presented here, but I also extracted information about research in deep learning. And you can see the same increase in academic publications in the domain of deep learning. And if you correlate or search for the combination of adversarial learning and deep learning, you can see that most of this publication actually deals with attacks on deep learning models. So some examples of the results of attacks on machine learning. One example is a spam detection system, which analyzes the content of the email in order to classify the email as spam or not spam or phishing. A spammer, of course, can manipulate his email and manipulate the content of the email in order to evade machine learning-based detection systems. Another example, attacks on image recognition systems, machine learning-based systems. For example, this one, I think from this year, researchers showed that deep learning or CNN-based image recognition model can be bypassed simply by adding stickers to the sign and making the machine learning model think that the sign is not a stop sign but another one. This is another example. Banks or organizations want to automate the process of processing checks and without human intervention. And in this case, a simple manipulation on the check can actually result in that the algorithm will identify the numbers of the amount in the checks differently, and it will be difficult to observe it by just looking at the check. This is another example from an older research from 2014. Machine learning is also being used to identify malicious profiles in social networks. In this case, crowd turfers, which are the opposite of crowdsourcing. Crowd turfers are a group of profiles that try to abuse the network and together to influence the network. And in this research, it was shown that the behavior or the content of the crowd turfer can be manipulated such it will be able to evade those detection mechanisms, or even if I know that the machine learning system is using the data or collecting data now for training a model, the crowd turfers can actually inject their behavior in such a way that afterwards, when the model is trained, it will not be detect the crowd turfer correctly. The attacks on machine learning can be categorized by different attributes. The first attribute is the goal of the attacker. Either compromise the confidentiality, the integrity, or the availability of the model. When we are referring to confidentiality, the attempt of the attacker is to expose information about the model or about the data that is being used, and he can do it by querying the model or applying in order to see the results. Some models complete by themselves different features, so I can use querying the model in order to complete missing attributes, missing information, and so on. I can compromise the integrity of the model by manipulating the input in order to make the model classify the input incorrectly. This is called evasion attack. Or I can, if I have the ability to affect the training process or the training data set, I can inject my own data in order to make the algorithm learn wrong concepts, and this is called a poisoning attack. Availability attack is an attack that is conducted mostly in the operational phase, after the model is being used, in order to compromise the quality of the model, the accuracy of the model, the performance, or in general the access, the ability to use the model. Like in the first example of causing the autonomous vehicle to stop by sending specific inputs to his sensors, or an allergy attack in which I can influence the training set in a way that, for example, in intrusion detection systems, when I analyze network traffic, most of the legitimate traffic will be blocked. The second attribute is the knowledge, the pre-knowledge that attackers have on the machine learning system. The first option is a white box attack, which the attacker has all the information or partial information about the data sets or the algorithm itself or its configuration. And in this way, an attacker can easily analyze the model, like in the example for 2014, and to understand, for examples, which are the most sensitive features that can be influenced, and then craft and create its own samples. It is not always unrealistic to assume that the attacker will not have the information about the model, because in some cases, like in smartphones, we can apply machine learning models on the smartphone itself, and then we have access to the model. The second option is a black box attack in which the adversary has no knowledge about the model. And what we do assume is that he has the ability to query the model. And based on querying the model, he can infer different information that can help him in conducting the attack. This will be the second part of my talk. I mentioned also this attribute before. An attacker can conduct his attack during the training phase. And in this case, he can compromise the confidentiality by having the ability to read, for example, the data set, which might be sensitive. Or during the training set, he can inject information, modify the data sets, or influence the actual training process by manipulating the algorithm itself. The second option is conducting the attack during the operational phase of the model when it's being used. And in this case, already mentioned some of the examples, you can query the model in order to infer information about the model. It can help him to evade the model. It can help him into stealing the model in cases of machine learning as a service. And I also mentioned denial of service attacks. And the last attribute is whether the scope of the attack, whether it's a targeted attack for a specific, he has a very specific goal, or a more general, broad attack just to influence the correct behavior and compromise, for example, the integrity of the model. So after this introduction, I would like to present a work that was conducted by Ishai, who was the previous presenter. Ishai is a PhD student supervised by me, Professor Yuval Elovich, and Professor Lior Rokach. And Ishai, he mentioned that he's working in Deep Instinct, which develops methods and tools to detect attacks or malware using deep learning techniques. Ironically, in his PhD studies, Ishai is trying to evade such systems, and as you will see in the reminder of the presentation, he managed to do it very successfully. So the attack that I'm going to present is a black box attacks against classifiers, machine learning classifiers that are analyzing malware, or specifically analyzing sequence of API or system calls that are recorded by Sandbox that Ishai also mentioned. So as you already probably know, machine learning is being applied for many years to detect malicious code, either by applying static analysis, information that is extracted from the code itself, and provide indications about the behavior of the application. This is the basic assumption. And since not always we can observe the actual behavior of the application by analyzing statically the code, dynamic analysis actually provide a complementary approach in which we observe the behavior of the application while it is running, either in a sandbox or the user computer. And different kind of information can be utilized in order to understand whether the application is malicious or not. Recent academic research, and also, as Ishai already mentioned, companies and anti-malware products are utilizing machine learning and deep learning algorithms in order to detect new attacks. And the scope of the research, as I mentioned, is to see if such advanced algorithms can be evaded. The specific focus is the dynamic analysis or AI-based antiviruses which specifically analyze sequences of system calls. This is the vast majority of the behavior of vast majority of antiviruses. They analyze the system calls in order to understand whether the application is malicious or not. This approach has been researched for many years, and the representation of the application based on system calls can be by using n-grams as features, applying Markov models or other sequence analysis algorithms, and recently neural networks or deep learning based algorithms. So a quick overview on the process. We have the inspected file. The inspected file is executed for a specific amount of time, usually a few minutes, in a sandbox. Ishai mentioned the Cuckoo sandbox, which we also used in this research. The output of the sandbox is a JSON report, which provides all the information, including the system calls executed by the application. This sequence of system calls are being transformed into the required representation in order to feed to the classifier, and the classifier analyzes this sequence and provide the decision whether the application is malicious or not. So our assumption that we have a dynamic analysis classifier which used in our research Windows API calls, including system calls. Our goal is to be able to modify the application in such a way that it will be classified as benign by the algorithm, and also we do not want to sacrifice the correctness or the malicious functionality by when we manipulate the code. Our assumption is that this is a black box attack. The attacker does not have any information about the model itself, but he can query the model. He can provide him a sequence of system calls extracted from an application and receive the results, the classification from the model. The attack that I will present is a two-step attack that exploits actually a property which is called transferability property, which was shown for specific cases that if I'm creating for one model, if I'm creating an adversarial example which is not classified correctly by one model, it will probably be classified the same, mistakenly classified the same by another model which with the same goal, even if the models are being trained with different data sets. So we exploit this property in order to create a surrogate model which tries to, which is actually an approximation for our black box model. And in the second step, based on the model, the surrogate model that we learned, we are using it in order to create the adversarial examples, the adversarial files. This is a more visual illustration of the process. So actually we have the black box model. We have synthetic cases that we are generating. We are querying these synthetic cases. We're querying the model with these synthetic cases in order to get the model classification. And we are using these data sets in order to train a machine learning algorithm and to create our reverse engineering model, the surrogate model. And during the second phase, we have a sequence of system calls. We are adding or replacing system calls in the sequence until the surrogate model classifies this malicious application mistakenly as benign. Okay, this is the general process. In more detail, in the first phase, in the phase that we generate the surrogate model, we start with a small sample of files that we know their classification. And iteratively, what we are doing, we are generating based on these samples, labeled samples that we have, we are generating synthetic samples. We are generating synthetic samples in a way that we are making the examples move towards the boundaries of the surrogate model. So we want to be able to learn the boundary, the classification boundary of the model itself. This is for the first step. Just for the evaluation, just in this case, this process is repeatedly done, starting from this small set of examples. In our experiment, we learned the surrogate model based on a little bit more than 2,000 examples, while the Blackbox model was trained on 360,000 examples, and we were able to approximate the model and execute the attacks eventually. In the second step, when we have a system call, a sequence of system calls that we want to classify, we select randomly an API call, and we replace it, continuously replacing it in a way that we are using the surrogate model, again, to make the example move faster or closer towards the decision boundary of the model. And this allows us to actually make the attack very efficient with a minimal number of changes to the system calls. So I don't have much time, so just to the results. We have just the results. We have a data set containing 360,000 sandbox report for the training set, and 36,000 reports for the test set. You see here the configuration of the surrogate model. We used, actually this recorded sequence of system calls can be very long. On average, it was 100,000 system calls. We analyzed windows of 140 API calls, and if one of these windows was classified as malicious, the application is classified as malicious. You can see here the basic performance of the classifiers, a large set of classifiers that was evaluated. Very high accuracy for most of them, especially for the deep learning algorithms. However, when we conducted the attack effectiveness shows the percentage of malicious software that was previously detected correctly by the models. However, it was misclassified after the manipulation. And you can see here the percentage in the second column. You can see the percentage of the API calls that was required to being added, a very small amount of API calls. In order to show that this attack is actually practical, we also developed a framework which we call the Gadget. This framework actually allows us to conduct the attack very effectively without any access to the source code. It is based on a wrapper DLL that can be added to any application, Windows application. This wrapper DLL receives from the attacker, receives a configuration file which instructs him how to inject API calls based on the decision process into the application while it is running in the machine. And in this way, we managed to show that we can practically evade the detection mechanism. So I think I will stop at this point, and thank you.
Okay, thanks. We are late in time, so we have only one question, but it must be a very good question. So let's not, it's very good or just good? It's very good.
Thank you very much for the interesting talk. What did you learn about what kind of models are more robust to this kind of attacks? Do you have any conclusions about how to create detection models that will be robust to attacks?
So there are due to the short in time, I didn't reach the slides that talks about how to protect against such kind of attacks. There's research being done on attacking machine learning models, but also defending. Based on the results, you can see that the most robust algorithms are not the deep learning, the most complex ones, which are more vulnerable to this kind of attacks. But there are different methods in order to make the algorithms more robust for adversarial learning.
Okay, thank you.
Thank you.
Now